Hey guys, welcome back. This time around we're going to continue our discussion on the language of chemistry. Previously we looked at elements and atoms, and we said that an atom was the smallest functional unit of an element that displayed all of its physical and chemical characteristics. We find a number of atoms of elements in our body. Frequently we find them dissolved in water. In this case, they typically will have a net charge to them, and we call them electrolytes. Three types of electrolytes that are found in our body are going to be sodium, potassium, and calcium. We find, though, that these same atoms of elements will chemically bond together to make larger structures. These larger structures are known as molecules. There are two types of molecules found in our body. There are molecules of an element, in which we find that two or more atoms of the same element chemically bond together to make a molecule. An example of that would be oxygen. Oxygen gas has two individual oxygen atoms chemically bonded together. Another type of molecule is going to be a molecule of a compound. In the case of a molecule of a compound, we will find that we have two or more atoms of different elements chemically bonded together to make that molecule. An example would be water, H2O, in which we have two atoms of hydrogen and one atom of oxygen chemically bonded together. Another example would be sodium chloride, in which we have an atom of sodium and an atom of chlorine chemically bonded together to make a molecule of sodium chloride. And the final example that we'll give here would be a molecule of glucose, in which we have 6 carbons, 12 hydrogens, and 6 oxygens chemically bonded together to make a molecule of glucose. We would know this as our molecular formula. It's the combination of atoms it takes to make a molecule of glucose in this case. Now, it is true to say, though, that where an atom is the smallest functional unit of an element with all the physical and chemical characteristics of that element, it is fair to say that a molecule is the smallest form of a compound, in which you will see all the physical and chemical characteristics displayed. Let's take, for example, water. Now, if you think of the physical characteristics of water, it's fairly neutral, and we can frequently use it to dissolve things in. But it's not very reactive. You can't burn it, you can't blow it up. But now, if we were to break it down any further, we would find that we would break it down to its hydrogen ions and its oxygen ion. Now, hydrogen goes boom, and oxygen burns. Now, we will frequently find that the compounds are going to be physically intermixed. Now, if we have a situation where two or more compounds are physically intermixed, we have something known as a mixture. And notice I used the word physically intermixed. There's no chemical bonding that's going to occur between the compounds in this mixture. They're only going to be physically intermixed, which means at any given time, I can physically separate the compounds from one another. All I have to do is use some kind of physical means, such as evaporation or filtration. Think of the story that you may have learned in history books. Gandhi went to the sea to make salt. In reality, Gandhi really was not making salt. What he was doing was taking salt water and evaporating the water and isolating the salt. And when he did that, he isolated the salt in its purest form. And that compound is 100% pure. Mixtures can be described as either homogeneous or heterogeneous mixtures. Homogeneous means that each of the compounds within the mixture are equally dispersed throughout the mixture, meaning that I can take 2 samples from that mixture and I am guaranteed to find the same concentration of each of the compounds in each of the samples. Heterogeneous, on the other hand, the compounds are not equally distributed throughout the mixture, meaning that if I take 2 samples of the mixture, I would not be guaranteed to find the same concentration of each of the compounds in each of the samples. There are actually three types of mixtures. One is solutions, another one is colloids, and the third one is suspensions. Before we can describe the differences between these three types of mixtures, we have to identify two new terms. One is solvent and the other one is solute. Solvent is going to be the compound with the highest concentration in the mixture. Solute is going to be the compound or compounds with lesser concentrations within the mixture. Now, in the purest sense, then, if we're looking at these mixtures, solutions are going to be mixtures in which we have a homogeneous state, in which all the compounds are equally dispersed throughout the mixture. Colloids and suspensions are going to be heterogeneous mixtures. The difference between those two, though, is will the solute separate out if given the opportunity. In the case of colloids, the solutes may be heterogeneously dispersed throughout the mixture, but they will not settle out. In the case of suspensions, though, when given the opportunity, the solutes will separate out of the mixture. An example of a suspension would be blood. If you think of blood, you've got water, and then you've got the blood cells suspended in it. Now, as long as it's in our body and moving, and our heart's pumping it, it will stay in the blood cells will stay in the mixture. But if I take a sample of my blood and put it into a test tube that's unhybridized, I will find over time that the blood cells will start to settle out or separate out, and we'll have two different layers. And one layer is plasma, and the other layer would have the blood cells in it. Now let's briefly talk about these solutions a little bit more. We're talking about solutions. We can describe a solution one of two ways, either percent solution or molar solution. And what's the difference between a percent solution and a molar solution? Well, it's how you make the solution. In the case of a percent solution, the best way to describe it is take your graduated cylinder and say I want to make a 10% sodium chloride solution. First thing I would do is go to my chemical shelf, and I'll pull a bottle down that's got the compound sodium chloride in it. Because remember, compounds can be separated out physically to their purest state and then stored, and we can store sodium chloride away in a bottle at 99.9% pure state. I would take that bottle over to the counter where I have my graduated cylinder, and I would pour into the graduated cylinder the sodium chloride until I got enough sodium chloride to bring it up to the 10 milliliter level in that graduated cylinder. Then I would go and get water, and I would finish filling up the graduated cylinder to 100 milliliters with water. That gives me a 10% sodium chloride solution. So I could do that with any compound that I have on my shelf and make a percent solution. We find that percent solutions are found quite regularly in the medical field. Think about it. If you look at IV bags, it's going to be 0.9% saline solution. Now notice with these solutions that the solute is usually what's going to be used to describe the solution. Solvent's never going to be used to describe a solution unless the solvent is something other than water, because water is the common solvent in the human body. How does that differ from molar? Well, if I want to make a molar solution, I have to know what the molecular weight is of the molecule, or what the weight is of the given atoms in that molecule. Now, how would I do that? Well, now let's go take a look at the molecular formula of glucose. It's C6H12O6, which means I have 6 carbons, I have 12 hydrogens, and I have 6 oxygen molecules. First thing I'd do is I'd go to my periodic chart, and I would see what the atomic weight is of each of my elements here. Carbon, as you can see, is 12. Hydrogen, you can see, is 1. And oxygen, you can see, is 16. Then I would multiply each one of those times the number of atoms that are of each element that is going to be found in this molecule. There's 6 carbons, 12 hydrogens, and there's 6 oxygens. 6 times 12 is 72. 12 times 1 is 12. And 6 times 16 is 96. Add all that together, it should give you right around 180. Now, if I go ahead and say that 180 grams is equal to 1 mole of glucose, and if I want to make a 1 molar solution, then what I would do is I would weigh out 180 grams of glucose. Again, it's a compound, so I can get it off my chemical shelf. And I would add it to a final volume of 1 liter of water to get a 1 molar solution. Now, why is 1 molar solutions more effective than percentages? Well, the thing with a 1 molar solution is that it's repeatable and it's more accurate. It actually brings it down to the value of what we call the Avogadro's number, in which we would have 6.02 times 10 to the 23rd molecules of solute per liter of water for any compound I want to make. So if we're looking at real precise drugs, we would want to do those in a molar solution. If we're looking at diluting our solution into a larger solution, such as IV fluid diluting into our blood system, then we can go with percentages, because with percentages, we're not guaranteed to have the exact same concentration each time, but in the ballpark. Now it's time for you to do some reflection. I want you to go back, think of the terms, think of energy, think of forms of energy, think of matter, think of what elements and atoms are, think of what molecules and compounds are now, and think how we can build these solutions. You have a fantastic day. See you later.